Welcome. We present MVGBench, a comprehensive benchmark for multi-view generation models. Given some condition and camera poses, multi-view generation models output images at packed views. These images can then be further used for 3D composition. These models have been the foundation for 3D content creation. This includes text to multi-view and single image to multi-view generation. There has been exciting advancement in this field, with more than 30 papers popping out in the last 2 years. However, important questions such as how good is the actual performance or what makes a multi-view generation model good are not answered. Comprehensive analysis requires proper evaluation, yet existing evaluation is problematic. Methods are usually evaluated by computing 2D matrix between ground truth and generated images. This is not suitable for generative models as the result can differ from ground truth but still be self-coherent. Furthermore, it does not consider 3D consistency and relies on 3D ground truth, which makes it difficult to evaluate on real images. Another problem comes from diverse training setup. This leads to different optimal input condition per method, and it is difficult to report a fair comparison with classic evaluation. As an example, in ThinkJumor paper, 0123 is worse, while in S3 paper, 0123 is even better. To this end, we propose MVGBench, a comprehensive evaluation suite for multi-view generation models. Our suite consists of comprehensive matrix and different performance aspects. Our evaluation matrix consists of 3D consistency, image quality, and semantic consistency. Our first contribution is a novel 3D consistency matrix. The idea is to compute 3D consistency while self-consistency in 3D. Given single image and target cameras, the multi-view generation model outputs multi-views, which are then divided into 2 view sets, and we feed 3 Gaussian to each view set. If the images are perfectly consistent, then the 2 3 Gaussians will be very similar. Hence, we use the discrepancy between 2 3 Gaussian as the 3D consistency of multi-view images. We measure the transfer distance and errors between random 2D images. Our matrix do not compare against ground truth, which is suitable for evaluation of generating models, and we can report results on real images. We can also fairly compare between methods. We also evaluate the image quality and semantic consistency using large vision language models. We curate datasets to evaluate 3 performance aspects. First, that setup performance. Second, generalization to real images. And third, logarithms to different elevations, light intensity, and zoom angle changes. We evaluate 12 state-of-the-art methods on different synthetic and real image datasets. The first observation is that there is a trade-off between 3D consistency and image quality. Some methods generate good images but bad at 3D consistency. Other methods are good at 3D consistency, but quality is suboptimal. Most methods lie under the bottom left part of the consistency and the quality plot. More recent video-based methods achieve better balance, and our method leverages the best practices and achieves the best 3D consistency. We show one example here. 0123 generates images that look good independently, but are not 3D consistent. ThinkJumor generates 3D consistent images, but the quality is suboptimal. Our method leverages the best practices and balance better in consistency and quality. We show more examples on real image dataset. We can see that 0123 images are very inconsistent. The ThinkJumor has texture that does not look pleasing. And our model balances better on both dimensions. Another observation is that all methods now produce lower image quality results. This leads to another finding that there is a large gap between synthetic and real images, especially in image quality. Another discovery is that some methods are not robust to input perturbation, such as light intensity as shown in this example. The output varies a lot given small changes from input. Please see our paper for more analysis. We also investigate the design choices of multi-view generation models. What makes a multi-view generation model 3D consistent? We categorize the design choices into 4 aspects. First, how the target camera poses are embedded into the network. And second, how is the input image encoded as conditioning? Third, how the target view features interact with each other with different attention mechanisms. And finally, how much data does it need to train a good multi-view generation model? We find that both RCN and CAPE help improve consistency, and RCN is slightly better than CAPE. However, when combining with a convolution encoder, the difference is very small. For input image encoding, we find that both Dino and ConvNext are better than the CLIP feature encoder. Here, we show one example. CLIP encodes image as a global feature vector, leading to Breuer structure. In contrast, ConvNext encodes images as feature grid, preserves more fine-grained details. Another question is the data amount. In this table, we can see that the performance changes a lot by increasing number of objects from 10,000 to 50,000. However, moving forward does not change too much. Hence, we conclude that 50,000 objects are sufficient to perform well on synthetic data. However, more data does improve the generalization to real images. Thank you for watching. Our code, pre-trained model, and the evaluation suite will be publicly released.